Hello, my name is Lorena, and today I'll be presenting our recent work named Contrastive Instruction Tuning, which is a method for enhancing large language models' robustness against variations in instructions. So nowadays, with the help of instruction tuning, large language models have demonstrated remarkable abilities in instruction following. But are they completely good at following instructions yet? Based on recent studies, the answer is no. These models are often very sensitive to how the instructions are formatted. Let's start with a simple example. So suppose you're writing something and you want the model to help you to check your grammar, so you pass the sentence together with this instruction. So as helpful as one makes best, the model says is acceptable, which is the correct answer here. However, if you paraphrase the instruction and say the same thing just in a different way, models like Llama can give you a completely different or even a wrong answer. And this is just one simple example. Recent works have shown that if there are slight variations in instruction formatting, models like Llama 2 can experience a performance difference of up to 76 accuracy points. And if there are typos or usage of synonyms in instruction, even models like ChatGPT can give inconsistent answers. So LLM's lack of robustness in instruction variation causes these models to be very unreliable. Then what should we do? So to address this problem, we propose contrastive instruction tuning. The high-level idea is that in the language model's hidden representation space, we want to encourage semantically equivalent inputs to stay close to each other, while dissimilar ones to stay far apart, so that the model will produce similar outputs for similar inputs and be more consistent and accurate. So let's say we first have an instruction and the input instance from a task. So here the task is to check whether one sentence entails the other or not. And after we pass this input to the model, obtain the hidden state of the last token, and then just, as usual, use cross-entropy laws to encourage the model to do the correct next token prediction. Then we create the positive sample by paraphrasing the original instruction, while still using the same input instance. So we encourage the hidden states of these two data points to have high cosine similarity. This will encourage the model to recognize that the same instruction with different formulations can have the same meaning, so that the model can output more consistent answers. We then create a negative sample by randomly choosing an instruction instant pair from a different task. So here the task is grammar correctness checking. We encourage the negative sample to have lower cosine similarity with the original and the positive samples, so that the model can better capture the fact that the negative sample is semantically different and thus produce more accurate response. However, during training, we observed that the contrastive loss converges quickly if we just select negative samples from a different task, and this observation is also consistent with the findings of an existing work. So they found that LLMs are already able to distinguish instructions from different tasks such that their cosine similarities are already very low. So to collect hard negatives, we draw inspiration from near out-of-distribution samples, which are data that are from the same task but with different classes, and they have been shown that are less distinguishable. So accordingly, we select negative sample that share the same instruction as the original one, but is paired with an input instance that has different outputs or different user intents. So for example, if the label token for the original data is yes, then the label token for the hard negative is no. So overall, our approach encourages the model to align semantically equivalent instructions with different phrasings, while contrasting inputs with different user intents, so that the model can produce more consistent answer when giving syntactically different but semantically equivalent instructions. So just to quickly go over our experiment setup, for training, we use data from the Flank collection, and we use approximately 52,000 instruction instance pairs. And for every pair from the dataset, we create positive sample by randomly selecting a predefined instruction template as a way to paraphrase the original instruction. So here we only consider paraphrases because we want to avoid making assumption about specific types of variations in instructions, and a robust method should be able to generalize to other types of variations. And for negative sample, we randomly select another pair from the remaining data set. And for the model, we use Alpaca LoRa, which is a llama model fine-tuned on instruction tuning data that is automatically generated via self-instruct. So for evaluation, we randomly select 300 instruction instance pairs from each of the 10 glue datasets, and then we select 6 clean instructions predefined for each task, and we add perturbations on 4 different levels, including character level, which introduces typos, word level, which uses synonyms, sentence level, which adds a randomly generated sequence of 10 alphabets and digits as distraction, and semantic level, which paraphrases the original clean instruction. So we guarantee that all of these instructions are unseen during training, and we report the average accuracy and standard deviation over all of these data. So we evaluate the base model, which is the Alpaca model itself, the continuous instruction tuning, which is the base model fine-tuned on the same data as our method, but without the contrastive loss, and COIN, our method, on 5 groups of instruction across all these 10 glue datasets. So as can be seen from the graph, the base model has very low accuracy and high large performance variance, which show that the model itself is very sensitive to instruction formatting. And for a continual instruction tuned model, although it shows increasing accuracy, which is expected as the model has been trained with more data and more steps, it still has a 6.1% performance gap, meaning it still lacks robustness in variations in instructions. But then compared to continuous instruction tuned model, our method, COIN, has consistent improvement in accuracy and decrease in standard deviation without introducing any new data and training steps. And we reduce performance gap, and given the training dataset only introduces instruction paraphrases, COIN is able to generalize from one type of variation to all these types of variations in instructions. And to understand the impact of our method, we also visualize how the hidden state change. So as can be seen from the left figure, the representation of instructions with different perturbations are clustered into almost distinct groups. This may indicate that the model is treating syntactically different but semantic equivalent inputs to be different, and thus it's more sensitive to how the same instruction is formulated. In contrast, our method, COIN, so in COIN's representation space, these data points are less distinguishable, and this shows that COIN effectively aligns the representations of perturbed instructions to those of the clean instructions. So as a result, the model becomes more capable at capturing the original semantic meaning of the instructions and less sensitive to variations in instructions. And we also analyze our method's impact on different tasks. So as can be seen from the model, COIN does have a positive impact on all these tasks, and with more evident improvement on paraphrase identification and grammar correctness tasks. So intuitively, these tasks can benefit more directly from COIN, which aims to enhance the similarity of representations of semantically equivalent instruction input pairs. So in conclusion, we propose contrastive instruction tuning that aligns hidden representations of semantically equivalent instruction instance pairs. And our evaluation results show that COIN does effectively enhance models of robustness to instruction variations. And in the future, our method can be applied to enhance models' robustness on other prompt components, such as system prompts, few shock demonstration, and also other settings that involves other modalities. So these are the QR codes to our paper and our code. If you have any questions, feel free to reach out to me via email or Twitter. And lastly, I want to give a special thanks to all my amazing collaborators. And that's all for Contrastive Instruction Tuning. And thank you for listening.